An important relationship in analyzing bars under torsional loads is the connection between the internal torque and the shear stresses on the cross-section. And we already have an expression that tells us what the torque is given the stresses, but it's often important to know what the stresses are given the torque, and I'd like to go ahead and develop that relationship. Now, just as an aside, this is the same thing as asking, well, given R of x, so the internal force on a cross-section, what are the normal stresses on the cross-section? And the way in which we developed the relationship for that was we started with the definition that R is equal to the integral of sigma dA, and then we went ahead and integrated. So in the homogeneous material case, this integral is sigma A, and I can then solve this for sigma and find out that sigma is R over A. And so I'd like to go ahead and first look at the homogeneous case for the torsion question, and then we'll go ahead and look at the inhomogeneous case for the torsion question too. So that'd be like the composite bar case or something of that nature. So let's go ahead and start with the basic relationship that says that the torque is equal to the radial position times the shear stress is integrated over the area. And let me go ahead and first substitute in the constitutive law. So we'll go ahead and say that the shear stresses tau are equal to G times gamma. So we make that substitution first into the system. And now we can go ahead and substitute in for the shear strain, which is R d phi dz. So we'll end up with an R squared times the shear modulus times the twist rate integrated over the cross-sectional area. Assuming the homogeneous case, I can pull the g and the d phi dz out from underneath the integral sign. So I'll have g d phi dz is equal to the integral of r squared dA. And this integral r squared dA we usually call j. It's known as the polar moment of inertia. It's just a property of the cross-section. So that's an integral over the cross-sectional area there. And so we end up as a final result is that the torque is equal, well, not a final result, but an intermediate result, that the torque is equal to Gj times d phi dz. Okay? And this actually is going to allow me to get back to the question of what the shear stresses happen to be if I happen to know what the internal torque is, because the twist rate is related to the shear strains, and the shear strains are related to the shear stresses. So the first thing I'm going to do is solve for the shear strains, or sorry, the twist rate, in terms of the torque. So the twist rate is equal to the torque divided by Gj. And that tells me that gamma is going to be equal to the torque times the radial position R divided by Gj. And now I can write down what the shear stress is by multiplying gamma by G. So the shear stress tau is equal to Tr over J. So this is the counterpart to my sigma is equal to R over A. It's a little bit more complicated now because it's not just the internal resultant applied to the system divided by the geometric property of the cross-sectional area. It's also multiplied by radial position along over the cross-section. And that's simply because torsion is more complicated as a state of deformation than just simply pulling on a bar with an axial force. If I were to plot my result here, I'm going to find out that the shear stress tau as a function of radius is going to be a straight line here, and the maximum value of the shear stress is going to be T times the outer radius, capital R, divided by the polar moment of inertia, capital J here. And just for reference, the values or expressions for J, if you have a solid bar, it's going to be pi r4, or pi r to the 4 divided by 2. Or if you had a hollow tube, it would just simply be the difference of the fourth power of the outer radius to the fourth power of the inner radius multiplied by pi over 2. So those are two useful expressions for solving problems. Now this is the case where the bar is homogeneous. So in the homogeneous case, we're able to have this equality here where we've pulled out the g from underneath the integral sign. If you don't have a homogeneous system, then you have to leave the g inside the integral there, and you get a slightly different result. So let's just look at that real quick. So if I have g is now a function of r, then it's going to have to remain inside this integral sign. I can still replace for gamma here. And so I can replace for gamma, I can write it as r d phi dz. And now I can take a half step forward and pull out the d phi dz. but I have to leave the g inside the integral sign. And so what I'm going to do is I'm going to take this whole integral here, r squared g dA, and I'm going to call that gj effective. So that's what this little EFF is for. Okay, so the result then is that the torque is equal to gj effective times d phi dz. I can again solve for the twist rate. It's going to be t divided now by my effective gj. And so my shear strains are going to be t times r divided by my effective gj. So the shear strains are still linear on the cross section. And the shear stresses will now be tr times g as a function of r divided by gj effective. And the variation of tau with respect to r is going to be proportional to r times g as a function of r. So it really depends on what the how the cross-sectional properties vary radially to know what the variation of the shear stress on the cross-section is as a function of r.